So welcome everyone, and thank you for joining us for this new episode of the Meet the Specialist webinar series, which is dedicated to bakers and millers to gain a deeper understanding of quality control of flour in particular. So the episode of today will be focused in improving the relationship between baker and miller based on a single flour and dough analyzer that you can see on the screen here, which is the Mixolab. So during the presentation, if you have any questions, please use the question and answers option and do not hesitate to write anything that comes to mind. Let's start. Just to start, I would like to give a little bit of context about the world in which we are living, into the bakery and milling world, and also about the quality control world and how it has evolved in 100 years since the 1920s. So here, this is just an image of what was a miller here and what was a bakery 100 years ago. And this is the same image here, but in the 70s. And this is what we have now. And I think that here the most relevant conclusion, or the most obvious conclusion, is that we have gone from an artisanal know-how that was managed by people knowing what to do and how to do it, to really industrial challenges. Especially because everything from the miller side and from the baker side, everything has been strongly automatized. And because of that, there is less and less people working on the line of production at the miller's level, but also at the baker's level. And because of that, the expertise is no longer so present in the companies, who are relying more and more on the flour quality. And at the same time, if we focus on the flour quality control, just to give a little bit of feedback of history as well of what to do. Since forever, we have been producing flour thanks to stone milling. And it was only in 1879 that the first roller mill was invented in Hungary. And because of this invention, millers in particular, they had more and more possibilities to control the quality of their flour, to make blends of wheat or flours, to correct, to adjust according to what was necessary for such and such production. Because of that, they needed instruments to control the quality of their flour, a little bit better than just looking visually to what was happening. The first one of those tests was the cheddar test, and it was to measure a little bit more objectively the quantity of proteins that is in a flour, a little bit more objectively than just looking at the dough, at the gluten network. And then during the two World War, so during World War I and II, we have seen the appearance of a lot of different materials to qualify the protein quality on one hand. So you have the alveograph, you have the farinograph, and of the starch on the other end. So here you have the amylograph that was invented roughly at the same time. And just at the same moment, approximately in 1916, you had the creation of the AACC, so the American Association of Cereal Chemists, who aimed to propose a unique way to use those methods. So basically everyone could use the same method and everyone could compare their results to each other. In 1955, there was the apparition of ICC, which is kind of the same thing as AACC, but at more European level. And in the meantime, we have also seen the apparition of the folding number, for instance, or the Rio to control the proofing characteristics. And then there is a second step that is more called the legacy, where not a lot of true innovation were made, but a lot of progresses though, because in 1970 we have saw the apparition of the glutamatic, which is basically a better way than to look at the protein quality that again just stretching a dough. Big revolution, NIR method, but it was in 1980. So if you just consider that, it's not so long ago. It's only been 45 years. So that's quite recent still. And NIR is limited to composition, protein content, humidity content, but it's not purposed to describe quality. Then we have had basically evolutions of those pre-existing devices, and then a second revolution here, which is the Mixolab, which is one of the only quality control instrument in the world that is able to analyze both the protein quality, but also the starch quality. So what does this history tells us? First thing is that most of the tools that we use today, they were invented 100 years ago. If you ask yourself why the alveograph test at constant hydration is made at 50%, it was because it was the standard water absorption 100 years ago for making breads from flour. Today is no longer it's no longer the case. The protein have evolved, the wheat quality have evolved, and of course, as you have seen from before, the industry has evolved a lot. But still, we are using the same method that were designed 100 years ago. And plus those laboratory tools that we have seen, they were mostly designed not for bakers, but for millers, mostly for millers to help better understand their flour, but mostly to ensure consistency. The purpose was not really to make the most adapted flour for one baker, but rather to ensure consistency, to always provide the same quality of flour. Because bakers, they hate that. If it's one day good and one day bad and one day good and one day bad, this is terrible for them because they have to adjust all the time. At least if it's always average, then they always correct the same way. So yeah, the purpose here was to ensure consistency. And at the time, there was this second line of defense is that bakers, they could count on experts, on master baker, able to correct if the flour was not 100% fitting the process. So by experience, and because they had a lot of expertise on this specific process and on this specific product, they were able to shift the process a little bit to change the water absorption or to change the water content or to change the mixing time or the proofing time or the temperature of the oven by 2 degrees. And they were always able to obtain a conform final product in the end. But I will come back to that. This expertise now, those master bakers, they are more and more difficult to find and to keep. Plus, as we may have observed, the baking industry is becoming more and more complex. We have observed a strong automatization of every product, of every production line. Plus, there is not only that, but there is a strong need to produce different products. 20 years ago, you went to the bread shelf in the supermarket and you had like one type of bread. Now you have whole wheat, you have gluten-free, you have clean label, you have organic, and then you have enriched in fibers, you have protein packed, and so on. So there is a strong need from the final consumer to evolve, to innovate. And so that means using more and more different raw materials, including also enzymes. Enzymes have grown to be extremely popular in the last 100 years, and that adds an additional variation. And then finally, the customers, the final consumers of the product, us, we are more and more demanding about the quality, about the availability, about all of that. But more than that, we have a real way to not to annoy, but to complain. Like if tomorrow I'm going to the supermarket and I'm buying the same biscuit as I always do, and I find it weird, I can very easily go to any social media that I want and complain. And surely I will be joined by other people who will complain as well. And so together, all of a sudden, we can have a big power to well, not to annoy, but to express ourselves. So companies, they have everything to they cannot afford to have customers' complaints now. So they really have to master final product quality. So obviously this situation is getting less and less sustainable. And I think this is very well expressed by a few different facts. The first fact is that the traditional parameters that we always use, they are finding their limits. When I was in school, I heard a lot of easy ways. I heard a lot of generalities. And I think this is the same everywhere, whatever the school. Easy ways such as the formulation for white sandwich bread. Well, you need to use a flour protein content that is between 10 and 11.5%. That should be very easy. So I just need a flour with protein content between 10 and 11.5 to make a good bread. The reality is that it's not the case. Here we have made a study involving 150 wheat from all around the world, and we analyzed them for protein content and for volume. So we made the bread, and we analyzed the flour, and we made the bread. And what we can see is that, that there is a slight tendency. So protein, yes, is important, but if you take 10% protein or 11 point, it's not even 11.5, it's 11.1 protein percent, then you can end up with two very different volumes. So again, protein is important. I'm not saying the opposite, but it's just one part of the picture. It's not the entire puzzle. But still, what we observe when we go visiting customers, when we ask our customers what are their specifications, most of the time we hear about protein content, gluten content, farinograph, alveograph, extensograph. And sometimes we always, well, of course, ash content. Ash is, let's say, between 0.4 and 0.6. So that's very, very limited in terms of functionality. You may find some Hackberg index, so falling number, but the rest is completely focused on proteins. So that should mean that if we have proteins under control, then it should be enough to ensure that we have bought we are produced, or we have bought the best adapted wheat or the best adapted flour for our final product. And this is not the fact. This is not the fact, because between the flour and the final product, there is the process. And the process is extremely important. This is why when we see advices on the literature or on specific websites that says that to choose a good flour for making pizza, then you need a W value of the alveograph between 300 and 340. Again, that's a tendency, but that doesn't work. That doesn't work for every bakers, because it does not integrate, one, the specificity of the end product. I'm talking about a pizza. What kind of pizza? Is it a pizza from Napoli, or is it a pizza from Chicago? Because most probably it will not be the same thing. And if it's not the same thing, it might not require the same flour quality. So the final product already impacts a lot the flour quality that we need. And plus there is the process. And for the process, you have many variables. You have the formula and the recipe. You have, of course, the process itself. How long does it take for mixing, for proofing? You have the different machines. You have the different temperatures that we use, the different times. We have, in the end, also the human factor. Sometimes we can see differences between the day shift and the night shift, just because the master baker at the day shift is not working the same way as the master baker in the night shift. Because of that, we strongly believe that the flour quality should be specific to each baker. It cannot be generic. It should take into account the process specificities and the final consumer preferences. And then there is another thing that is very important, is that the expertise, the master bakers that we could found in the bakeries 100 years ago, they are leaving. And this is a tendency that has accelerated a lot since COVID. those expert people, they are retiring, they are leaving the industry, and it's very complicated to find and to train a new master baker that is willing to stay for 10 years, the necessary time to get this expertise, this know-how. Oh, I'm touching the dough and I know how to react. So expertise is leaving the baking industry. So we need to rely more and more on the flour quality. And all of that leads to a very important fact. And this is the result of a survey that we have conducted on LinkedIn a few months ago, just asking a very simple question. Does it happen that flour, despite meeting all laboratory specifications, still gives issues during baking? And 96% of operative bakers have answered yes. Yes, I have my flour within my specs, but still I have issues on the line of production. For some of them, it can go as high as, for 25% of them, so 1/4 of bakers, it happens very frequently, more than 1 out of 10 deliveries. That's a lot, and that's a lot of work to correct. So that's very annoying for the bakers, but that's also very annoying for the millers who have spent a lot of time making that the flour can enter into the specifications. So I do have specifications, it still does not work. Interestingly enough, 4% of people have declared that no, it never happens. And when we look at who are those people who answers no, it never happens, they are mostly academics. So those are the people writing the study saying that you need a flour protein content between this and that to make a good sandwich bread. So that's a lot of theory. In theory, that should work. The practice says otherwise. And so here, excuse me. Here, what does that mean? That means that there is a lot of things that we can do. And to do that, we need to shift a little bit the way that we are doing things. We need to go from tradition to something a little bit more modern. And to do that, the best option here is to use the Mixolab, which is truly one of the best innovation in the last century. Because you need to start with the end quality in mind. Baking bread for consumers. What we do here, what we propose, is that we want the final product to always be perfect, to always be conform, because in the end, this is what the final consumers value. We want this little boy here to ask mommy and daddy to buy the same product again. And here the keyword is same. I want the same texture, I want the same color, I want the same everything. And to be able to achieve that, then the baker must have his process under control. And to have its process under control, then he needs to work with an adapted flour quality. To have an adapted flour quality, the milling process must be under control. And to have a milling process under control, then you need a good wheat quality or an adapted wheat quality. So that means that there is a lot to consider, a lot of variable. And here we need to consider a multifactorial approach. So the idea, our proposal, is to stop guessing. Stop analyzing the flour with hundreds of methods for a result that is the baker saying it's not adapted. Here, we need to stop predicting, stop guessing, and start knowing. And to do that again, we propose a little bit of reverse thinking, going from the final product to the wheat in the end. And to do that, this is a little bit the base of our series of webinar. The first one was about defining and objectively measure what is a good final product. Then, once we know that, we need to objectively assess the behavior of the dough during process and design efficient specification to select the flour. Specifications that will allow us to not have this situation where 96% of the bakers still declare having issues. And then, thanks to those specifications, millers can focus on producing compliant flours with the baker's COAs. And finally, because they have efficient specifications, then they can efficiently select high-quality wheat to produce compliant flour with optimal behavior during milling process. And the good news here is that KPM Analytics has an entire range of products that can help replying to all of those objectives. First step, about the final product, we have a great offer by iPro and by Cycline in particular, and you can find a summary of this webinar, well, the recording of this webinar online. You have the address here. But for today, we are going to focus on how objectively, and here this is really the key word, how to be objective. Objectively assess the behavior of the dough and design efficient specifications to select flour. And we are going to do that based on one instrument, the Mixolab, which is a universal dough and flour analyzer. This is truly one of the real innovation in flour quality control of the last 50 years, and we will see how. The first thing is to know, what do we measure? So basically here we are producing a dough and we are mixing it between two blades, and we are measuring the resistance, the necessary strengths to run those blades always at the same speed as a function of the consistency of the dough. So what we measure here is the evolution of the consistency of the dough during mixing, but also during different temperature phases, during heating and then cooling down. This can be related to the evolution of the dough consistency during the process, first during mixing, and then during baking, and then during cooling. This is what we are doing here, sort of replicating the process. Why do we do that? We do that to get access to a maximum of data. We have seen that most of the specifications, they have been built a lot around proteins. And so this is not necessarily a surprise to see that we have a lot of unhappy bakers, because flour is not just proteins. Not saying that proteins is not important again, but 70% of the flour is starch. And there is very limited control on starch behavior. This is totally outside of our control. So here the concept of the Mixolab test was to have within one test the protein behavior, but also the starch behavior and their interactions and the impact of enzymes. So to get access to a very comprehensive, complete information about the flour quality in only one test, one fully automated test. So this is extremely simple to run. The operator time is maybe 10 minutes and the test time is 45. That works with a small amount of sample, which makes it also very usable by anyone in the cereal field, not only millers and bakers, but also breeders, for instance, using a standardized method at the international level. So how do we make it work? How do we make a test with the Mixolab? That's again very simple and fully automatized. So there is not a lot that the operator must do. Let's say that the average training time should be around half a day, because basically you just have to configure the test, select your protocol, enter the water absorption capacity, the moisture content of the flour, and just follow the instruction of the software. Weight the corresponding amount of flour, and incorporate this flour into the mixing bowl. Just place the nozzle to inject the water into it, and that's it. And you're good to go for 45 minutes. What we obtain in the end, this is a curve. Well, this is actually two curves. We have a temperature curve here that we see in red, and we have a consistency curve. So this is just the evolution of the consistency of the dough, depending on mixing and depending on the evolution of this temperature. Because of that, we are going to access a lot of information about the water absorption, the effect of mixings, but also how the protein denaturates during heating, about the starch gelatinization, about the amylase activity, and about the starch retrogradation. all of that, that's a lot of information. And we need to go a little bit in depth regarding this curve because there is a lot that we can see here. First of all, there is the first part of this test. The first part of the test lasts 8 minutes. And during those 8 minutes, we are running the test at constant temperature, so 30 degrees during 8 minutes. During this time, we are going to observe the same type of information as a farinograph, meaning that we are going to see the water absorption capacity, the development time, the stability, the weakening, and all of that in 8 minutes. So this is what we know, basically. This is how the protein behaves during mixing. This, we have it. What is interesting is that this is only 18% of the Mixolab test. So we have an additional 82% of information that is completely unique to the Mixolab. And this phase here, in particular, is completely unique to the Mixolab. And it's how the protein reacts to the increase in temperature. So here we start heating the dough with a gradient of 4 degrees per minute. And when we do that, we observe a big drop in consistency. Basically, what we see here is how the protein resists to the dual action of mixing and of temperature increase. And basically, this can be related to the to the oven spring, to the moment where you place the dough into the oven. It can be a bread dough, it can be a biscuit dough. There is still this first phase in the oven where you have to increase the volume, to gain a lot of volume. So that works for bread, but for cookies, then you need to have a nice cookie spread, which happens basically at the same time. And to do that, you need a protein that is able at the same time to expand, but also to resist deformation. And this information, you can find it here. Because basically, if you have a protein that does not resist well to the increase in temperature, if you have a weak gluten, then you will see a big drop in consistency. And that can be related to, for instance, in the oven, to a bread that is rising in volume, and all of a sudden, the gluten doesn't have the capacity to resist the deformation anymore, and it collapses. Or if we are speaking about cookie, the cookie is spreading too much because the gluten doesn't have the capacity to resist. On the contrary, if you have a very resistant gluten, so a very flat curve, not a big decrease, then that means that the gluten is resisting a lot to the heating. And that might lead to a gluten that does not allow the bread to rise, or that doesn't allow the cookie to spread. And because of that, in the end, you will have a non-conform product. If we speak about bread, in both cases, the volume will be bad. But it will be bad for two opposite reasons. Knowing that it will be bad, it's already a very good information. That is, again, completely unique to the Mixolab. Knowing why it will be bad, it's even better, because that means that we are able to correct. We are able to anticipate. Is it about strengthening the gluten or weakening the gluten? We can do something. And then we reach a phase where the temperature is about 55 to 65 degrees. So we reach starch gelatinization. So this is this big increase here in the curve that we observe that is related to the bread volume and to the creme structure. Here we might think that it looks like sort of a viscograph or Hervier curve, the beginning of a viscograph or Hervier curve, but there is a big difference between the Mixolab and the Hervier or the viscograph, is that we work on a dough, not on a batter. And that's very important because bakers work on a dough and not on a batter. And a dough is a place of an intense competition for the water. Every component, proteins, gluten, starch, fibers, they are competing to access the water to develop their full potential. And they cannot because there is not enough water for everyone. So here, working on a dough and not on a batter will be a better representativity of what is happening in reality. Here we are observing the starch gelatinization in a structure, in a system that is closer to what the bakers do every day. So again, more representative. And then we have the gel resistance. Here we are working at very high temperature at 90 degrees. And during this time, we are going to observe a drop in consistency. So we have created a starch gel. And this starch gel resists more or less to the dual mixing and at high temperature constraints, stress. So that induces a loss of consistency, which is mainly related to the amylase activity. If you have two flour exactly alike, but with two different amylase activity, this is mostly where you will see the impacts at this area. Of course, this is not just about amylasic activity. We can also see here impacts of the damaged starch content, of the interactions between proteins and starch. But again, here to simplify, this is a phase that is related with amylase activity. And then finally, we are cooling down the dough. So we are cooling down the dough with a gradient of -4 degrees per minute until reaching 50 degrees. So here, basically what is happening is that we are simulating what is going on when the bread is getting out of the oven. When you take the bread out of the oven and you eat it 30 minutes later, that is the greatest bread in the world. It is still warm. This is delicious. The crumb is soft, and that's perfect. And then you let it on the counter, and you come back 2 days after that, or a week after that, or 3 weeks after that, depending on the final product, and the bread will have turned hard. And this is due to starch gelatinization. This is due to the fact that starch is trying to come back to a crystalline position. That's the scientific explanation. The simple explanation is that if we see a big increase here in the torque, then that will be related to an intense retrogradation. And that leads to a shorter shelf life of the final product. On the contrary, if we have a very flat curve, limited increase, then that means that the starch retrogradation is long, is not intense. And so that the final shelf life of the product will be longer. So that's a very complete information that we get with the Mixolab on a curve that has been qualified in the past as complex. It seems complex to retrieve all the information because this is going up and down and up and down. And the name of the parameters are sometimes not so self-explanatory. We are working with a C2, C3. What is a C2? What is a C3? That is sometimes unclear. So this is why we can simplify this curve. We can simplify this curve to better see the quality, to have a better visual representation of the quality. So basically, we take the curve and we simplify it on indexes. So on 6 indexes that are graded from 0 to 9. And for those 6 indexes, we are able to design a profile that corresponds to the acceptability of one process. So a green area here is a representation of what is good for a specific process. So this is just a way to take the different phases, the water absorption, the mixing behavior, the gluten behavior when we are heating the dough, then the starch gelatinization, the amylasic activity. For all of those parts, we are transforming the curve into a profile. And that gives us a very visual tool of the quality of the flour, a visual representation of the quality of the flour. And then we are able to develop a target profile that again will correspond to the acceptability of a specific process. To create a profile, a target profile, that is actually very simple. You do not need a PhD, you do not need complex skills. You just need to be able to observe. to select all the flowers that are giving good results at the line of production. So no issues during production, no stickiness, no extensibility problems or whatever, and that are giving a good final product. You have those flowers, you analyze them with the Mixolab, so we recommend to have a minimum of 20. And then you can use the integrated software to define for each of those flowers, each of those tests, what was the minimum and what was the maximum for each index. Once you have that, you have your profile. The only thing that to make an efficient profile, you need two things, two very important things. You need a good communication between quality control and production, between miller and baker. You need a good exchange of information, because if you are analyzing a flour that is not perfectly working and putting it in the mix, then you will a little bit screw up the database. So you need to have a good database, and to do that, you need to have a good communication. That are the two things: good communication and a good database. And so, of course, in the end, if you are designing a profile that corresponds to various final products, here a pizza, a croissant, or a pan bread, you will end up with very different flour quality, as it is expected. We already know that. We know that for making a croissant or a pizza, we don't need the same flour quality. What is more a surprise, or not a surprise, but that really confirms everything that we have said from the beginning of this session, is that even if you make very similar final product, and here those data, those are real data that they have been built for the same company that are producing in different countries the same final product, a pan bread every time. But if you are in Brazil, in Germany, or in Australia, you don't have the same processes. You don't have access to the same weights. You don't have the exact same formula, the same recipe. And because of that, you are going to need different flours, not slightly different, sometimes very different flours. So again, this is why we strongly believe that we need to better fine-tune the flour quality according to each process, and that we can no longer count on generalities such as you need protein content between this and that. Here, I would just like to give you a short illustration. This is an example that has been made in collaboration with a pan bread manufacturer in Brazil. So the first step was to determine the target profile. So here we analyze 21 process-adapted flours to define the maximum and the minimum for each of the indexes. So we have the profile. The second step, very important step, was to validate this profile with new flours, new incoming flours. On 21 new incoming flours, 15 have been identified as okay. Good performance during process, final product okay. And 6 were identified as non-performing because something happened during the process or because the final product was non-conform. And so the idea here is to see, where do I discriminate? Where do I see the difference? And if we look at the absorption index, for instance, so the first index that is about water hydration, what we see is that between the green dots that corresponds to the good flours and the red dots that correspond to the bad flours, we have no discrimination. So we need to look further. If we look at the mixing index, discrimination seems a little bit complicated as well. Every bad flours are basically inside except one, but it's really not far away. And it's really when we start heating that we can see some differences. Here, we are able, with the gluten plus index, we are able to start discriminating. With the viscosity index, we are able to discriminate, and so on. And in the end, we are able to summarize the results in a table like that. So here in black, you have all the performing flours with, for all indexes an indication as this flour has been identified as inside the profile or as outside the profile. And what is very obvious is that we are able to discriminate all non-performing flours because all of them, they had a minimum of 50% of the indices out. We are also able to identify most of the well-performing flours. So here, 10 on 13. And we still have, of course, a part of uncertainty that corresponds to 3 well-performing flours that have 1 or 2 indices out. So here, our partner, they were making baking tests on all incoming flours. Now they can select which flour they are going to work on. They don't need to work on those ones because they already knew they are okay. They don't need to work on those ones because they already knew they are not okay. So they just need to make baking tests on those 3 ones. That is way less work. And another important information is that the first 2 indexes about the absorption and the mixing, they are not discriminative. They are not able to identify what is good and what is bad. And this is only by heating the dough and by going further, considering not only the protein quality, but also the starch quality, that we are able to have a true discrimination. So this is where the value of the Mixolab relies. And this is why here, by building this profile, bakers and millers can enhance their relationship by really focusing on what really matters. And then there is a second step that you can perform. You can go further with the Mixolab by controlling not only the flour, but also the dough behavior at the line of production. How does that work? Well, basically, you just need to take a sample of dough. It can be at the end of the mixing step, which is generally key, but it can be also at different other steps. Analyze this dough using the Mixolab. And for this dough, you can even create specification and know if it's a good dough at this step or a bad dough that will lead to a bad final product. We have 2 types of testing here that we can apply. We have the instantaneous consistency analysis, which is just about mimicking what the baker is doing on the line of production, meaning touching the dough and evaluating if it's more or less hard, more or less stiff. So this is a test that is very short, that lasts only 2 minutes. And during those 2 minutes, we are only having this information about how hard the dough is. Then we can go further again, and we can make a full test with temperature changes, which will lead to way more information that we still need to understand. Just to give you a couple of examples here, so those are real studies that we have done with real partners. Again, the idea is to take a piece of dough from the line and insert it, into the Mixolab. And I do not have my video working, and I don't know why. Okay, that's okay. We'll check that. But again, the idea is that you make a piece of dough, you stretch it a bit, and you can incorporate it into the Mixolab and just analyzing the consistency of it. And here, this is a study that we have made with a bagel, donut, sorry, not a baker, donut manufacturer. Here we have analyzed good doughs that were giving good final products, but also they were having an issue with the donuts closing after frying, after baking. The hole in the middle was disappearing, and that was really problematic for them. And so here the idea was to analyze the dough, and by doing that, just by observing what was giving a good donut with a good hole and a bad donut with a bad hole, we are able here to make objective discrimination, not based on the feeling of an operator, but actual data, actual numbers that you can put on what is good and what is bad. same manufacturer here, they were having two different lines of production for making the same type of final product. Everything was the same. The flour entering, the recipe, everything was the same, except that for line A, they had a very old mixer. And for line B, they have a very recent mixer. As a result, the final product that we're producing it, following the exact same recipe on both lines, it was not the same. By using the Mixolab, they were able to show that because of this mixer, they needed to target a different consistency on line A and on line B to have the exact same final product in the end. And then again, you can go further. You can analyze the dough during a longer time. Here, this is just an example. This is a test that we have performed here in our lab on 6 different dough samples, same recipe, same everything, just the amount of water that was changing. What we have observed is that one, there is a strong relationship between the dough hydration and the torque measured at 2 minutes. And that's already very important because that means that a baker can rely on the Mixolab based on a certain consistency to know how much water it needs to add to reach a target consistency. So that's already very interesting information. And then you can let the tests run for a longer time and you have access to a full dough profile. This dough profile is showing us that there is not only differences in the initial consistency, there is also differences at every part of the curve. So hydration does not only impact the initial consistency, it will impact the behavior of the dough during the entire process. Having this information can be key, can make the difference here between a good product and a bad product. And here, again, just an example about what a curve with a full recipe can look, what the shape of a full recipe can be. And as you can see, it has nothing to do with a standard wheat flour curve. It's completely different. Here, those tests that they were performed on an Italian line of cracker production. So this was for making crackers. And they had a very long resting time, about 7 hours. And we have analyzed the dough after 1 hour, after 2 hours, after, so this is what we see here, 1 hour, 2 hours, 3 hours, 4 hours, and so on. And we are able to see variations. First, we are able to see something, which is a very good first news. But also we are able to see differences during this resting phase, differences on the protein side and also differences on the starch phase. And we are able to make hypotheses to link that to the recipe. Because here we see the impact on the protein phase, and we know also that there were proteases inside of the mix. And so we can suppose that this decrease in the torque here is related to the impact of the protease during the resting phase. And then we have an impact here during the starch phase. And we also know that there were amylase in the mix. So here, this is just an hypothesis. What I mean is that it opens our possibility, because here we are able to observe something, we are able to see something, and knowledge here is key for the future. Being able to measure is being able to improve. And the Mixolab, the beauty of the Mixolab is that it's a very versatile tool. So whatever your formulation, we can analyze, and we have made tests on many different raw materials, many different final products, and we are able to analyze a lot of different things. So here, just to show you a few examples, this is absolutely not a complete list, but we have worked on pulses, on gluten-free products, on keto formulations, on a lot of enzymes and raw materials. So this is a very versatile instrument. So I think it's time to conclude here. And the main message is that we are convinced that the traditional approach, which is to make a lot of different analyses, farinograph, the extensograph, the alveograph, the folding number, the glutomatic, and this and that and that. Millers and bakers are making a lot of tests to make sure that their flour is compliant. And then you have that, and usually you also have a consultant of some sort or literature that tells you that because it has a protein content between this and that and folding number between this and that, this is a great flour for making croissant or for making pan bread with honey milk, because this is logical. The results of that is that we have 96% unhappy bakers. So we need to change something. We need to change the paradigm and to go further and to maybe change a little bit the way that we see things, the way that we do things. And the easiest way that we have is to do some reverse thinking, is to go from the end product to actually measure the process, real performance, thanks to vision inspection systems, then to understand how the recipe and the process impact the final product by analyzing the dough characteristics objectively, not with a master baker that is touching the dough, but with objective number. Thanks to that, we are able to defining what is the best quality flour according to the process. And because we have this image, then we can provide, the baker can provide the miller an objective measurement, an objective target, an objective area that he needs to reach to make sure that everything will be okay, thus allowing the miller to really focus not on 1,000 different parameters that maybe do not matter so much, but on what actually matters. Here, the idea is that what you can measure, you can improve, and the Mixolab is a very interesting tool for that because it measures the entire flour quality, not only gluten, not only starch, but the combination of both of them, plus fibers, plus enzymes, plus the interactions between all of that. And plus, to conclude here, we can see that all of those instrumentations, all of this process provides us with data. And data is the opening of the future, because data is the food for artificial intelligence. And artificial intelligence is growing, is getting more and more important, and is going to reach our companies. If we have data, we will be prepared. So having this data can really change the future for all of us. And on that, I would like to thank you very much for your attention, and I would like to welcome any questions. I will go to the Q&A now, but just so you know, if you need any further information, do not hesitate to contact us in the future. You have the addresses here, and we will be very happy to help and to discuss the best that we can. So thank you very much. Questions now. So I do have a question. Is gelatinization intensity related with starch retrogradation? So that's a good question, and I have to say that my knowledge about starch is not enough developed to answer, but I suppose yes. I suppose this is here an assumption because this is the same starch during gelatinization and during retrogradation. But gelatinization and retrogradation are two different phenomena. I think that one can impact the other, but I'm not sure. I can check and come back to you. Then I have another question about the phase where we analyze the amylase activity. It also probably will indicate starch damage and protein behavior. So it's in one system of flour, we can relate all these three factors together, or only each one or two of them only. My understanding of this question, please let me know if I'm wrong, is that you would like to know what do we see in the fourth area where we see a drop inconsistency. The Mixolab doesn't explain what is going on. That's very important. The Mixolab is just analyzing the consistency, the evolution of the consistency. And then, because we know a little bit about flour and a little bit about dough, we are able to make a hypothesis and to check those hypotheses. So we know that stage 4 here is impacted by the amylase activity. But we have also seen evidences proving that the damaged starch impacts this area, and that the protein impacts this area, and that the types of granules impacts this area. So it's not only one factor, it's all factors together that will create this behavior. Again, the Mixolab doesn't tell you why it is happening the way it is. It just tells you it is happening this way. It's a little bit like the water absorption. The Mixolab tells you you have this water absorption capacity. It doesn't explain if it's because of the damaged starch or if it's because of the protein or if it's because of the fibers. It just tells you you have this amount of water absorption. If you want to go further and to completely understand, then you need to do additional analysis, such as folding number, such as a damaged starch, such as a protein content or quality, and so on. So yeah, that would be my answer. This is a little bit of everything that we see, and we have a tendency to make simplification when we talk, just for it to be easier to understand, but this is a global behavior. We don't necessarily need to understand, just to look and to say, this is different from this. And so it will behave differently in the production line. I hope I answered your question. I have another one saying, so from Pierre Molina here, is it correct to say that more water absorption in the dough, the lesser the retrogradation it will be? And if it's correlated? That's a very good question. That's a very good question because, yes, in general, if you put more water into a dough, then you will have less retrogradation. It will just softer the product. But retrogradation does not only depend on the water intake. It also depends on the starch properties by itself, like the types of granules and the interactions with the proteins. And if there is a lot of damaged starch, in the end, if the starch is able to retain the water, or the fibers are able to retain the water. So it's not only about water absorption, and no, here there is no direct correlation between the C5 and the hydration. They will be most probably a tendency of more water absorption, less retrogradation, but these are two different informations that we need to consider differently. So here, I hope I answered your question. Thank you, Pierre, for your thank you. Do you have any other questions? And of course, again, if you do not have additional questions now, that is okay. You can always reach us later on. Thank you very much for listening to me for an hour already. This has been great, and I hope to see you around for the next webinar where we will discuss what to do if we are not in the specs of the baker, which will be another fascinating topic. So I hope to see you then. Thank you very much, and have a great day or a great evening, depending on where you are. Bye-bye.